it's my pleasure to announce Joshua Wrigley from Università degli Studi dell'Insubria, from Lindenbaum, Tarski, Algebras to classifying toposes. Thanks, Joshua.
Well, thank you very much for inviting me. I'm going to share my screen. Can everyone see this? Can everyone hear me? Excellent, perfect. So yeah, the purpose of this presentation is to motivate classifying toposes. I've heard that during PhDs in particular, it can, as things get on, it can become a bit dragging. You start asking yourself, why am I doing this? Why am I here? What is the meaning of life? But before we get to those very big questions, I thought it would be good to come up with some preemptive justification for classifying toposes, in order to remind myself why I care about this particular branch of mathematics. And so the presentation is going to be me sharing some of my reasons for why I like classifying toposes. And in particular, we're going to, well, hopefully I'm going to convince you that we can think of classifying toposes as a universal way of dealing with the semantics of some very weird logics. We're going to look at how a very large class of logics can have classifying toposes. And in order to get there, we're going to use some intuition from propositional theories. In particular, we'll look at how categories generalize posets in the same way, very big air quotation marks around this, in the same way that first order logic generalizes propositional theories. And so yeah, we're going to be drawing this comparison between posets and propositional logic on the one hand, and categories and first order logic on the other hand. So the structure of the presentation is that every slide is going to have 2 points on it. The first notion is going to be a notion referring to posets and propositional theories. And then the second notion is going to be referring to categories and first order theories, right up until the very end, but there's a little technical interlude in order to justify some of the claims I'm going to make. But yeah, so the first obvious comparison we can make between posets and categories is that posets are examples of categories. And the meets and joins of the posets are examples of limits and co-limits within a category. So we already have this very nice generalization. But moreover, we can think about how we would add meets and joins to a poset in the same way that the usual notion of adding limits and co-limits to a category in the notion of taking free join completions or free co-completions. So the free join completion is 2 to the p op. That's going to be monotone maps from the order dual to the 2-element poset. When you order this pointwise, this is meet and join complete. And we've also got an isomorphism with the ideals on P. The ideals here, because there's no extra structure on P, the ideals at this point are just downsets of our poset. And we have an embedding from our poset into the ideals, which just sends an element to its principal downset. And this embedding preserves meets. And 2 to the p op is the free join completion in the sense that for any map F from our poset to Q, where Q is join complete, then we've got a unique extension. And we get precisely an analogous notion with that of pre-sheaf toposes. So when we take the functor category from the opposite of C into the category of sets and set morphisms, we end up with a complete and co-complete category, and the Yonader embedding preserves all limits. And the pre-sheaves on C is also the free co-completion in precisely the same sense that 2 to the p op is the free join completion. And so we've got a way of adding all meets and all joins in a way that preserves all of the meets coming from our previous poset, and a way of adding all limits and co-limits while preserving all of the limits of our previous category. But what happens if we want to preserve some of the co-limit structure? Well, for that, we need the notion of a covering system for post sets and Grothendieck topologies in the case of categories. Now, a covering system, as the name suggests, is going to give some notion of covering in the topological sense. And that is, it's going to assign to each element of our post set a family of downsets, which are going to be covering. And the properties that we require it to hold are respectively reflexivity, transitivity, and stability. So reflexivity is saying X covers X. B is saying if S covers X and Ry covers Y for all Y and S, then the union of the Ry's also cover X. And if S covers X, then and Y is less than X, then the restriction of S to things less than Y is also going to cover Y. And then with Grothendieck topologies, we get it's again a straight up generalization, except now we have more arrows between our objects. We have to be more careful with definitions. But A, B, and C on the lower definition are precisely analogous to reflexivity, transitivity, and stability. One important way of thinking about covering systems and Grothendieck topologies, which was mentioned to me, is that we can think about them as generalized inference relations. If a post set can be thought of as a weird propositional logic, then a covering system is going to be in some way encoding the inference of that logic. So we're going to have a subset, we're going to have a downset covering our element X if X proves the disjunction of S, is the sort of interpretation we would want to be aiming for. And so then reflexivity, transitivity, and stability then become properties that we would want our inference relation to have. And yes, so how do we encode the covering system in Grothendieck topology into our three join co-completions? That is through the notion of J-ideals and J-sheaves. So a J-ideal is an ideal in the previous sense in that it's just a downset, such that for every cover of X where S is contained in our ideal, then X is also contained in our ideal. And a J-sheaf is going to be a functor that whenever we have a covering sieve with a matching family for that covering sieve, then we have a unique amalgamation. Now, just initially, it doesn't seem like these two are entirely related. But if we remember back to the original isomorphism on the second slide, I think it was, a J-ideal is going to correspond to a monotone map from the order dual, which is J-continuous. And in that way, a J-sheaf is going to be a J-continuous functor, is the sort of idea we should be using to consider these. And then when we take all of the J-ideals and order them by inclusion, we get a frame. So a complete Hating algebra with all of the logical structure we could possibly want. And when we take the J-sheaves, we get a topos with all of the categorical structure we could possibly want. All limits, all co-limits, exponentials, sub-object classifiers. We have a lot of structure. Now, I mentioned at the beginning that there was going to be some propositional logic and some first-order logic, and I'm going to introduce that now through Lindenbaum algebras in the case of propositional logic, and syntactic categories in the case of first-order logic and categories. So a Lindenbaum algebra, to remind you, is a poset where the elements are going to be T equivalence classes of formulae. And the order is going to be syntactic proof in the theory T. And we're also going to give it a covering system where the S covers our formula phi if and only if phi proves the disjunction of the psi. And we also have a generalizing that, we have syntactic categories for first order theories. Now, being a first order theory, we have some variables that we have to keep track of. And so rather than just considering classes of formulae, we have to consider formulae in context, which is going to be pairs, x and phi, where x is a string of variables that contains the free variables of the formula phi. And then arrows between formulae and context are going to be equivalence classes of maps sigma from y to x, such that phi proves psi, and then this square bracket notation here represents where we've replaced every instance of yj in the string of variables y with sigma of yj in the string of variables x. If we have this syntactic proof. Now, what are the equivalence classes? Well, that's, we're going to say that two maps are equivalent if phi proves that they're equal. So yes, if you've come across syntactic categories before, this is not the usual definition that you find in the literature, but I'll come back to that right at the end. But I've introduced it as this because I think thinking about them in terms of substitutions of variables is a lot more intuitive. And it should also be noted that if your theory is multi-sorted, then the maps sigma y to x have to respect the sorts of the variables. And then finally, we've got a Grothendieck topology, which is very much analogous to the propositional case, which says that a family of a sieve generated by a family of maps gamma covers our formula if phi proves the disjunction, this disjunction down here. And the way of thinking about that is, if you can think about it in the way that the notation is suggesting that a formula in context can be thought of as all of the x's that satisfy phi, then a family of maps is covering if the images of those maps are covering. If you can think about these as sets, which they're syntactic things. And there's the another very nice description of the Grothendieck topology due to Johnston, which is that it is the smallest Grothendieck topology such that all of the sequence in the theory T are covering. And that's another nice way of thinking about it. And now we can finally arrive at classifying toposes, because we have our pose set and a covering on that pose set, and we have our syntactic category and a Grothendieck topology on that category. We can now take the J ideals on our Lindenbaum algebra and the sheaves on our syntactic site. And when we do this, we're going to end up with the notion of a classifying topos, a way of talking about the semantics of the geometric fragment generated by our theory. So if we think about what a model of a propositional theory is, it's not too exciting because it's just a valuation of the propositional variables, which is just going to be a homomorphism from our Lindenbaum algebra to the pose set 2. Or when we're taking the geometric fragment, the frame homomorphisms from the J ideals on our Lindenbaum algebra to 2. And so we end up with this equivalence between the frame homomorphisms and the valuations into 2. And more generally, if we were going to consider taking any frame as being the truth values that we want to consider valuations of, we have a natural equivalence between the frame homomorphisms and the valuations. Now, that's not particularly deep because the models of a propositional theory are just these homomorphisms, but it becomes more deep when we think about first order theories and their models in the category of sets. So we have an equivalence between the models of a theory T in the category of sets and the geometric morphisms from sets to the sheaves on our syntactic site. Now, a geometric morphism it's an arrow going in the other direction, which is co-limit preserving and finite limit preserving. And we get this equivalence between the models of our theory T and the geometric morphisms. And more generally, if we were going to consider models in any category, we get a natural equivalence shown there at the bottom. And so in this way, we are able to start off with any theory and be able to have a way of getting all of the semantics back out at the end by following this construction of a Grothendieck topos. But more generally, we can think about starting off with some very weird logic. You know, every poset can be thought of as some very odd propositional theory. And we would be able to, following the process I've described here, think about how we could arrive at the JT ideals on this poset. You know, we have an inference relation because it's coming from a logic. We arrive at the J ideals, and then this gives us a notion of what the semantics for the geometric fragment of the propositional theory should be. And precisely the same thing is going on with first order theories. So that's the way in which I think that categories should be thought of as a first order notion, in the same way that posets are a propositional notion. And then finally, I should mention that we can have some very some quite deep and profound equivalences on the topos theoretic level. So we might, two theories are going to be called Morita equivalent if their sheaf topoi, if their classifying topoi are equivalent as categories. And when that happens, it means that all of their semantics are equivalent. All of their models in sets, and indeed every Grothendieck topos, are equivalent. And so we've got this equivalence on the semantic level that might not be apparent on the syntactic level. We might have two different theories which, when you look at them syntactically, they aren't bi-interpretable, but their semantics are equivalent when we go up to the topos level. And so this can be a very deep and profound way of generating mathematical dualities. Now, very quickly, with my last minute or so, I just want to rush through some technical claims about the syntactic site that I made, because as I mentioned, it's not the usual syntactic site found in the literature. So in order to show that they do indeed generate the same classifying topos, I'm going to go through some dense subcategories. So when we have a site Cj, we say a subcategory is dense if the subcategory generates C with respect to this topology. That is, for every object, we've got a covering sieve, which is contained in our subcategory, and for every arrow, we've got another covering sieve generated by maps where the composite is in our subcategory. And when we do that, we end up with equivalent topoi. So yes, to remind people who've seen it before, the usual syntactic category is presented as this, where objects are formulae in context still, but arrows are now provably functional formula. That is, that they are formulae which satisfy these sequence, and they are taken up to provable equivalence. So I think that this is a little bit opaque, and perhaps it would be better to think about them as being given by substitution. And indeed they are. So yes, just quickly, the usual syntactic site I've notated by subscript T, and the substitutive one is notated with superscript T. So we've got a functor going between the two. preserves all of the formulae in context, and sends a substitution to this provably functional formula. And now I claim that this witnesses C superscript, here's a dense subcategory. It's subjective on objects, so the first condition to be a dense subcategory is satisfied. And then for the second condition, we can consider this diagram, and then we just do a little bit of syntactic logic, and this shows that it's a dense subcategory. This arrow here is dense by this sequent, and then by this equivalence of formulae here, we know that the composition here is in our subcategory. So yeah, don't worry if you haven't followed that. That's just to convince people who've seen syntactic sites before that substitution also suffices. There's a couple of references if you want to learn any more. And yeah, thank you for listening to me.
Thanks, everyone. Thanks to the speaker. Should we clap for the speaker? Anyone who has sound can do so.